Hello everyone. In today's presentation, we'll be talking about variation-aware automated routing and placement. It will be presented by Amin Shafi and Swarda Kulkarni, which will be done under the guidance of Dr. Mahadi. So, with the increase in complexity in the silicon photonic devices, it is difficult to manually place all the components and optimize the output. We have multiple challenges that need to be faced while placing and routing the components. The waveguide crossing and waveguide bends are the prominently observed challenges while integrating silicon photonic circuits. Nowadays, photonic circuits are often considered equivalent to circuit layout. Originally, the photonic circuits were manually laid out as a single non-hierarchical layout uh, consisting of multiple polygons. Some loss values are observed, uh, and these values in the are following. In waveguide crossing, we can find around zero point 0.1 to zero point 0.2 dB of loss. In waveguide bends, we can find around 0.001 to zero point 0.3 dB per bend loss. And in bulk waveguides, we find around 0.01 to 2 dB per centimeter loss. So what we want to do in this is that we need to minimize the total number of waveguide crossings and also the number of waveguide bends. The layout is built out of reusable hierarchical cells where some parts of geometry can be parameterized. Based on the design parameters, P-cell codes generates a set of geometric primitives on different mask layers. The resulting hierarchical layouts can be saved as GDSSI or OSS file, which are compatible. Today, the main automated variation process consists of design rule check, where layout is checked against design rules provided by the fab. These include specifications on space width, sharp angles, overlap of layers, which are unpredictable. These checks often reveal the hard to detect errors, such as minute misalignment between waveguides. As photonic circuits are sensitive, the geometric differences significantly from rectangular electronics to different. Uh, and The automated DRCs, that are the design rule checks, are not always trivial and often give results that are false positives. There is a recent developments with the new design related rule check are curvilinear structures and all angle polygons, which have steadily been improving this process. A variation aware routing is more important since the more detailed timing and variation information is available during the routing phase. For instance, correlated variation between lookup tables is only known after the placement phase, when the location has been fixed. Modeling of the variations and their correlations in routing and placement of the device is always needed. Some of the related work that we have observed and related to this project are in integrated photonics, process conditions such as exposed dose, resist age, plasma density lead to variations in device geometry, which affect the optical properties of device, such as its effective index, group index, coupling coefficients. These variations are propagated from device level to system level, which degrades the system performance. The process variability can be environmental, temporal, or spatial. And in this paper, we'll be dealing with the spatial variations. The next related work presented here is a tool which automatically routes and places the optical devices on a single layer. This tool is called as Proton Plus. This tool takes into consideration the routing challenges and minimizes the number of waveguide crossings, and as a result, reduces the insertion loss, and as a resultant, due to decrease in insertion losses, it will reduce the input power requirement of the photonic circuits. The third paper that we have referred is a thermal aware design and simulation approach, which is proposed. And the key techniques used in this are thermal sensitive optical power loss model, the thermal aware adaptive routing mechanism, and thermal aware simulation platform, which enables the optical network on chip simulations. The next paper that we have referred is a hierarchical method of characterizing the spatial variations by extracting the wafer level intra-die and inter-die variation components and their location dependencies on the variations. This method was explored on the silicon micro ring based on the optical transceiver application for architectural and the system level design optimization. The next paper we referred was a layout aware circuit modeling and variability analysis, which evaluated the circuit performance by combining the fast circuit simulator with circuit layout information and wafer maps, which are critical for designing the wavelength filter. This filter designing takes into consideration the variability extensions.
Good afternoon, everybody. In this part of the presentation, we are going to talk about the variation aware routing for FPGAs. We already know that as the feature size scales down in the integrated circuits, especially below the 19 nanometer regime, the impact of the process variations is more obvious than ever, and failing to have an optimal displacement and the routing between the components that we have integrated circuits would cause a real damage in power efficiency and timing. So the most important motivation behind this is to propose a variation replacement algorithm to improve the timing yields of FPGAs based on the developing statistical optimization techniques and by modeling the variations that we have in the circuits between the dies, intra-die and inter-dies in the ICs. Turning to a photonic integrated circuits layout, we already know that to define optical connections in the layout, the designer should draw a waveguides, and this is not such a trivial task, but as waveguides should respect a minimum band radius and spacing, some photonic design tools offer some tools to facilitate the waveguide creation, either by automatically or calculating the shift between the two ports, or by generating the shape from the simple path drawn by a user. Placement and routing is still a very manual process, and we have to dedicate waveguide crossings if it is required. So the approach that we are going to present here is the automated channel routing for integrated optics. But what is the channel? Suppose that we have a grid here. We have some devices on the integrated circuit that we have. These are the placement of the devices. And these are the channels, the places that we use to draw the waveguide between the devices. And we want to minimize the waveguide crossings and the waveguide bends as much as possible. As we can see, there is a proposed algorithm here. In the next paper that we investigated, they proposed a multi-purpose self-configuration of a programmable photonic circuits. In this kind of devices, we use a logic unit or a processor to obtain the self-configuration and auto-writing and characterization and the performance estimator. So by having this kind of chart, we can have an automated a self-configuration and a programmable photonic interconnects depending on the application that we have. For FPGAs, which stands for field programmable photonic gate arrays. In the next paper that I'm going to propose you is so much oriented towards to having the electronic interconnects and the optical interconnects together on the same chip. So having an optimized and optimal placement of the photonic devices on the chip and electronic devices on the chip, coupled together with the optimal placement of the electronic components is of importance. They use this kind of a flowchart to use the optimization technique. It is iterative process. It depends on the timing improvements that we have in the device. So let's talk about the objective of the project. The objective of the project is to develop a placement and routing algorithm that takes into consideration all of the fabrication and thermal variations, and to create a list of components with their intra-device variations, and also to optimize the inter-device connections to avoid variation affected areas on die, and defining optimization algorithms to optimize the inter-device and intra-device connections. The ingredients that we need to achieve these objective is fabrication process variation maps provided by the manufacturer. Again, the error maps provided by the manufacturer, and a device loss that we have in each device. So the main goals are going to be diminishing the signal loss in general. The method that we are going to use is, first we create a list of the devices, a net list of the connections, and also creating a library of the functions of each component, and place the components in a limited fabrication affected areas using some optimization methods, and calculating the loss of each device as they are without considering the system level, and developing such algorithm to do this task in an optimal way. And also we have to calculate the inter-device path with insertion loss and select the path with the least losses, and route the waveguide to avoid most variation affected areas while deciding the path. Then we perform the simulations, look at the results, and then if it is needed, we do the procedure all over again. So the tools that we are going to use is a MATLAB to develop the optimization algorithm, coupled with numerical FDDT and interconnects to observe the result as simulate the devices and the whole system together to perform the iterative optimization algorithm. And the procedure that we are going to follow is again based on the coupling between the two tools, and MATLAB and numerical tools, to perform the optimal placement and routing of the devices. So in conclusion, an algorithm to optimize the placement and routing of silicon and photonic devices was introduced by exploiting the components library and fabrication variable maps, and the inter-device channel routing considering the variation affected areas was done along with the minimum insertion loss calculation. And these are the references we used from the time period 2007 till 2020. And thanks for your attention and listening to our presentation. I hope you have a good evening.